Swayam Prabha. Digital India. Educated India.
Hello, good afternoon. So, welcome to the course on comprehensive view of speech processing, and today's lecture is 32 in series, and today we are going to discuss about the continuation whatever we are continuing from last two lectures, that is probability density estimation. And we have seen in last two lectures how do we estimate the density, the probability density from a given data. So, there are methods like parametric methods, non-parametric methods and semi-parametric methods. So, in the last class we discussed about the parametric methods, so in which the probability the probability density function will be estimated by using some known functional form, and we will try to estimate the parameters of a function by observing the data. So, that way the parametric form of probability density estimation can be carried out. And in case of non-parametric methods, we do not assume any functional form, and in the non-parametric functional form, the general methods that are used to estimate the probability density are kernel based methods and the k nearest neighbor method. And in the last class we discussed about the kernel based method, and we also introduced the k nearest neighbor. And as we have seen in the case of non-parametric approaches, the idea here is that in non-parametric approaches we do not assume any functional form at all, but at each data point we will enclose some volume, and we will try to see that in the volume how many data points are available, and with respect to that by using k by nv formulation we can able to estimate the density at each data point. So, likewise we can carry out the density estimation at each data point, and by linear combination of all these densities across all the data points, that gives you the overall density of the given data. So, that way in case of kernel based method we will assume some kernel function. So, that gives you the shape of the volume or the enclosure, and within that we will see that how many data points were there. So, with which you can able to estimate the density by imposing the kernel function at each data point, and we will try to see we will estimate the density around the data point using the method formulation as we have observed, the generic formulation of k by nv, where k is the number of points within the region and n is nothing but the total number of points we have tried out from the density function, and out of which k points are false within the region, and v is the volume of the enclosure region and all. So, that way even here in the k nearest neighbor approach also we use the similar approach, but here in the case of k nearest neighbor we will fix the value of k. That means here instead of fixing the volume, here we will fix the value of k, and we will try to like vary the volume such that the volume will be varied such that the volume contains the k points and all. Suppose if the density is more, that is if the number of points are clustered or if number of points are more in a particular the vicinity, so there the volume that is enclosed will be smaller. Suppose if the number of data points are very sparse, so at that time to achieve or to get k points within the enclosed area, so therefore the volume will be increased. So, that way here the k will be used as a parameter and k will be fixed, and to get a k data points within the volume will be varied. So, that is the idea about k nearest neighbor, and here this k nearest neighbor concept that can be used for estimating the probability density, and as well this k nearest neighbor can also be used as a classifier also. So, here we will see that how the k nearest neighbor can be used as a classifier. So, here for example, suppose the total number of data points in our data set is n, capital N, and out of that there are k classes in this data. There are k classes in the data. So, where this labeled as k equals to 1 to k, there are k classes, that is Ck, where C1, C2 up to Ck, there are k classes, and assume that Nk indicates that number of points belongs to a class Ck. That means suppose N1 indicates that the number of data point in the out of capital N, n1 points indicate that the number of data points belongs to class 1, n2 means the number of data points belongs to class 2. So, likewise nk indicates that number of points belongs to class ck, and as we know that the number of classes are k. So, therefore, the total number of data points is nothing but the summation across the data points belongs to all individual classes like k equals to 1 to k nk. And now, here as we have seen in case of probability density estimation, so we will try to estimate the as per the to perform a classification, we need to estimate the posterior probability belongs to each class with respect to each class. That means, posterior probability of each class we will try to compute, and that posterior probability will be indirectly computed by computing the class conditional density and prior probability and so on. So, therefore, here the probability density estimation is nothing but computing the probability density with respect to each class, that is probability of x given ck. So, here in case of k nearest neighbor, we will see that how do we estimate the probability of x given ck, or first of all how do we estimate the posterior probability. Once you have estimate the posterior probability for every class, it is nothing but we can able to perform the classification problem, right. So, therefore, here to achieve for estimating the probability of x given ck, right. So, what we do here is that since it is a non-parametric method, so we will generate a hypersphere around the data around each data point, for which the k data points will be falls within the volume, right. That is the way the k nearest neighbor concept where the data will be where the density will be estimated. At each data point we will try to increase the volume, we will try to vary the volume such that the k until the k points will be filled up within the region and all, right. So, therefore, there are assuming that suppose we created a volume such that there are k points within that volume, and among those k points, assuming that belongs to class ck, there are kk points are there in the volume. So, within the volume we have total k points are there, and within the k points, so if you try to analyze with respect to class ck, there are kk points are there in the volume. The total number of points are k, out of which kk points are corresponds to class ck. So, by knowing that, actually we can able to estimate probability of x given ck. Probability of x given ck is nothing but probability of the feature vector the given ck. So, these you can able to estimate. That means, here at the x we know that there are ck points were there are kk points were there out of k points. So, therefore, here probability of x given ck is nothing but, so within that volume there are kk points, the kk divided by, so with respect to ck there are total number of points corresponds to ck or nk, right, nk, and the volume offered is v. So, that way we can able to estimate the class conditional probability around the feature vector around the data point x can be carried out, right. Probability of x given ck is nothing but kk by nk into v. Well, because here out of k points, kk corresponds to class ck, and we know that the total number of points belongs to class ck or nk. So, therefore, kk by nk into v. So, this is the probability density, or this is nothing but the probability of x given ck, right. So, this way you can able to estimate that, and probability of x is nothing but, here in this case we are conditioned to class ck, right. So, if you remove this condition, then this becomes unconditional. So, the probability of x is nothing but k by nv. This is the generic way of estimating the probability density at a given data point, right, k by nv, because here we are not conditioned. So, therefore, here the total number of points within a volume are k, and the number of points in the total data set are n, and the volume is v. So, therefore, k by nv gives you the probability of x, and probability of ck is nothing but prior probability. So, in the data set we know that there are nk points belongs to class ck. So, nk by n gives you the probability of ck. So, by knowing all these terms, right, the individual terms, we can able to write the posterior probability of ck given x can be written as, using the base result, probability of x given ck into probability of ck divided by probability of x, and we know all these things from the given estimation. We can compute, we have all these values are there. So, if we plug in these values here, and we can able to see that probability of ck given x is nothing but kk by k. So, here probability of ck given x is nothing but posterior probability of a class Ck. So, likewise, so if you want to estimate the conditional probability, right, if you want to estimate the whether the given feature vector belongs to like which of the class, right, for a given test vector, feature vector, if you want to classify that test vector to one of the classes, the way we can able to carry out is nothing but we can able to estimate the posterior probabilities for all the classes with respect to a given feature vector, right. We can do that. So, that way you can able to estimate all posterior probabilities, and then once if you estimate all posterior probabilities belongs to classes, then whichever the posterior probability is the maximum, so that class label will be assigned to the test vector. So, that way this k nearest neighbor can be used as a classifier as well. This can be used for estimating the density, overall density, and at the same time you can use the k nearest neighbor directly as a classifier also, right. So, it is nothing but once you have a density is available for you, then afterwards for the test data we will try to see that what is the probability of Ck given x. It is nothing but just wherever, if you want to estimate the whichever the feature vector, if you want to estimate the class label of that. So, we will try to project that feature vector onto the density, and then around that density we will create a volume where there are k points are there, that depends upon the k nearest neighbor, and then in that k whichever the class is the dominating, whichever the class having higher number of data points, and that class label will be assigned to the particular test vector. So, that way we can classify the test vector or unknown feature vector for a given as one of the classes as per the posterior probability of that particular feature vector with respect to all the classes and all. So, that way you can say to minimize the probability of misclassification. So, the vector x is assigned to a class Ck for which the ratio of Kk by k is large. It is nothing but, so there are total k points are there, in that there are k classes are there. So, each class has some number of data points. We will try to estimate with respect to each class how many data points are there in the enclosed volume. So, whichever the class having highest data points, that class label will be given. And here in this case k nearest neighbor, there is if k equals to 1, it is known to be a nearest neighbor, one nearest neighbor classifier and all. It means that k equals to 1 means, so for a given at a given location, right. So, whatever suppose for example in case k nearest neighbor, the way the classification will be performed will be, so whatever the feature vector, test feature vector, so that is projected onto the probability density function, and nearer to the test vector. So, whichever the data point is there, the close by, where is the nearest data vector, and whatever the class of that particular the data point, so that class label will be assigned to the given test vector and all. So, there is not to be one nearest neighbor, because here k equals to 1. So, therefore, near to the data point, whichever the class label, whichever the data point is present, and that particular data point's class label will be assigned to the test vector, and that way the one nearest neighbor classifier with which you can able to perform the classification as well. And here if you look at here again, in case of k nearest neighbor, when you try to estimate the density for different values of k, as we have seen that as the k equals to large, you can see k equals to 20 if you assume for example, and you can see that the dotted line here is the actual true density. When you try to estimate this density using a k nearest neighbor, if the k equals to 20, so we can see that the achieved density will be something like this. But here you can see the true density is like consists of two Gaussians, like that means here we have a lot of data points, and again here we have no data at all, almost like very thin data, and again here we have again reasonable amount of data was there. So, therefore, when you look at the density function, the true density is something like this, right. We have it's like it's like approximation to the two Gaussians, like that means at two different locations the data concentration is more. And whereas if when you try to estimate that when k equals to large, k equals to 20, you can able to see that we can able to estimate only one density, only one Gaussian, right. Here no, actually here the data points are more, but due to as the k equals to very large, when you try to estimate the density, it is smoothed out. We are not able to capture this particular density, we are not able to capture this particular variation. So, this is kind of like k equals to 20, this is nothing but the bin width equals to large. In case of histogram, if you use very less number of bins or the width of a bin is large, then the estimated density will be smoothed out, right. That means the finer variations and density are not properly captured at all. In the same way, in case of polynomial fit, if you use a lower order polynomial to estimate the complex system, so whatever you see, whatever the data will be under fit, or you can say that the bias will be more. So the similar thing here also you can able to observe when your k equals to 20. And similarly, when k equals to 1, again you have other extreme. When you see k equals to 1, you can see the estimated density will be spiky or noisy, right. This is not the one expected. The estimated density will be like a smoothed one. You have a here and again here, this is the dotted one. But in place of that, when you put k equals to 1, where you have like, that means the enclosed volume will be just look at for only one data point. So that way when you try to estimate the density, you have spikes, that means you have a noisy, unnecessary like a transitions are present in the probability density, but that is not the expected one, right. And the other one is that there is the k is neither too large nor too small. When k equals to 8 or 7, you can able to see that the estimated density is somewhat approximation to the true density, approximation to. So that way here also, in case of k nearest neighbor also, the free parameter, the tuning parameter equals to k, the number of points k, the k should not be neither too large nor too small, right. K should be somewhat like in between, so that it properly captures the actual complexity of the system and all, or complexity of the probability density. Yeah. Now, the same thing here. This is like overall when you are using the non-parametric approaches, we have a smoothing parameters, as we have seen. Like in case of histograms, the smoothing parameters are nothing but, or control parameters are nothing but width of the bin or number of bins. In case of kernel methods, the controlling parameter is nothing but the width of a kernel, or nothing but the height of a hypercube or the side of a hypercube. In case of k nearest neighbor, it's nothing but number of data points. K is the tuning parameter or control parameter. And so what happens if you take a lower extreme where the estimated data the estimated probability density function will be over smooth, and it will be higher bias, and it's a poor estimator, right, we have seen. And similarly, if you don't provide proper smoothing, otherwise if you take the other extreme like hypercube volume equals to very small, or the number of data points are k equals to very small, if you choose it, then the inefficient smoothing, then you can able to see that have a larger variance, and the density estimated will be noisy, right. So therefore similar to the polynomial fit, whatever we have discussed, like the number of terms in a polynomial or the degree of a polynomial, it's neither be too large nor too small. Similarly, in case of neural networks also, you can say the number of units in a hidden layer and all. And now here you can see all these things where the likelihood, our approach, our overall goal is that whatever the probability, whatever the function, the probability density function we are estimating, its likelihood, it should be maximized. So the likelihood can be estimated like this. You can say probability of x, the given the kernel width, right. So here xn refers to the data point where n takes the 1 to capital N values. So assuming that all data points are independent, then you can able to estimate the likelihood as the product of the probabilities associated to individual data points, right. So this is the likelihood, and as we know that this likelihood will be maximized when h tends to 0, we have seen, because when h tends to 0, the probability density that will be estimated will be close to the true density and all, because it's a convolution of the kernel function to the true density. If the kernel function is impulse, then if you convolve the probability density function or true density with impulse function, then the outcome will be again the true density. But provided here the number of data points should be sufficiently large, that means as n tends to infinity, then the convolution of the impulse function with the true density results to be the true density, but that in practice it will not happen that way. So instead of maximizing the likelihood function, we know that we can able to design an error function, nothing but reciprocal of the likelihood function, and there is log likelihood, there is a negative of that, it's nothing but error function. And here what we are doing, this we are computing the mean of that. So, expectation of the negative log likelihood is nothing but expectation of the error function. So, for that, as n tends to infinity, by applying this is nothing but p of x into log p dash x, where p of x is the true density and p dash x is the estimated density. And now here we can the distance between the true density and the estimated density can be computed like this. The L is nothing but the log likelihood, the KL distance. This is nothing but the Px ln Px and minus integration of Px into like log p cap x, where p cap x is the estimated density. And this is nothing but this one. You can say, by simplifying this, you can say that log p of x minus log like p cap x, it's nothing but log, like you can say the p cap by p of x if you keep a negative over here. So, what it indicates here is that this gives you the distance between the true density versus the estimated density, and here you can see this is the estimated density, this is the true density, right. And here the difference between these two, the estimated versus true density, is weighted by p of x. It means that if the p of x is large, it means that there are more number of data points and all there, the whatever the distance is there, the distance will be maximized. We will try to give a more weightage for that. If the data points are very less, at that time, if the true density and the estimated density, if there are not matches also, but that is weighted by very less weight. So, therefore, if you what you hear, the KL distance is a asymmetric distance measure. It's not directly taking the difference between the distance between the estimated versus true density. Instead, it is weighted by the p of x, true density. That means, wherever the true density is high, then at that time the difference, the you can say the distance between the estimated versus the true density will be given more weightage, and wherever the p of x is less, it will be less weighted and all. So, this is known to be Kullback-Labrador distance, with which you can able to estimate the we can able to determine the distance between, or compare the two densities. That means, one is the estimated density, other one is the known density and all. The next topic which we are going to discuss here is that the semi-parametric approaches. So far we discussed about parametric and non-parametric approaches for estimating the probability density, and we know that each of them has pros and cons. So, like for example, here the parametric methods, so where they will assume some functional form and then with which for a new data, if you want to estimate the density, if you want to evaluate with respect to the particular probability density, it can be easily done, because we have seen the expression, the probability of x in case of Gaussian function, and in other case we can directly compute the probability of the new vector with respect to the given probability density function. That is easily can able to compute. In case of non-parametric method, there is no functional form, specific functional form, and the number of parameters grows with the number of data points. Number of parameters grows with the number of data points, because at each data point we will try to estimate the density. So, likewise at each data point we will try to estimate the density, and all these densities with respect to each data point will be summed up, or you can say the linearly you can combine them, like we will perform the superposition of all those densities, then that gives you the overall density of the data. So, that way the number of parameters grows as the number of data points, and it is also very slow to evaluate for new data, because when the new data for a given new data, if you want to estimate the probability density, the probability of the value, the new vector with respect to the probability density, that also takes lot of time, because there are several data points and lot of parameters. So, it takes lot of time to compute the evaluate for new data. In case of semi-parametric approaches, here what it will do is that it takes the positive aspects of these two things, parametric and non-parametric methods. So, with which you can see there is no as such, if you look at the overall probability density function, that is probability density that is estimated, it will not come under a single any specific functional form. But what we do here is that we will try to estimate the any arbitrary complex function, probability density function, with the help of some generic functions, with a multiple mixture of generic functions, That means, for example, if you try to assume that some hilly surface whichever is very irregular, right, and if you try to model that hilly surface, for example, So, one way is that actually here in using a semi-parametric approach, what we can do is that, so wherever you have like the peaks in the hill, where we will try to impose the Gaussians over there. So, that way whatever the irregular surface or the irregular hilly terrain, we can try to capture, or we can try to like estimate the density like by imposing the Gaussians with appropriate parameters at each point, at different points. So, that way even whatever the irregular surface or irregular the terrains, we can able to model that. So, the similar way here also in case of semi parametric approaches, the idea here is that the overall density is not using a single functional form, but instead we will use the multiple functions like known to be mixture of components, where each component corresponds to one generic function, and then the overall density is nothing but the superposition of all the functions put together and all. So, that way here the number of parameters grows with the complexity. It means that the depending that is the based on the complexity of that, we will choose the number of components and all. If the complexity is not much, even though there are lots of data points, if the complexity is not much, then we can use with a few functions, with a few mixture components itself, we can able to model the overall the data and all. Otherwise, if the complexity is very high, for example, then in that case we will use a more number of components, so that the number of parameters also will be increased. So, what I mean to say here is that in case of semi parametric approach, as such we do not use any specific functional form, but the number of parameters grows with respect to complexity. It is not grows with respect to data and all. If the really the data, underlying data is really complex, then the number of parameters will be more. And if the even though the data points are millions or billions of data points, but they are all very concentrated, they are not complex structure that is involved in the data points, then we can try to model that with a few parameters itself. With less complex functional form itself, we can able to realize that. So, how do we do that? For that we use the mixture models. We will see that what is meant by mixture models and all later on. So, and here again in case of semi parametric methods, it is computationally intensive, because a priori we do not know about the complexity of data. So, therefore, in an iterative way, by looking at the data, the complexity of the model will be can be observed, and with that the parameter estimation or the estimation of a density also will be varied and all. So, therefore, it is a bit of computationally intensive and all. Yeah. So, here we will see the in case of semi parametric approach, the way we will try to estimate the probability density will be given in the form of this flow diagram. So, here as I mentioned that these semi parametric models, one of the examples is the mixture models. So, here from the name, the mixture means here here in this case the probability density will be estimated by using some generic function forms, but here instead of using only one function, we use the multiple functions that depending upon the complexity of the data and all. As I mentioned, like for example, as we have seen earlier in the example, when you are analyzing the non-parametric approaches like histograms or like kernel methods or k nearest neighbor, as you have seen there is a one dimensional data. We have seen that the true density will be like that is given in the form of dotted line, which contains the data points are concentrated at two locations. So, if you look at the true density, what you can observe here is that you can see that the density will be more, or you can say that the number of points are located at two different locations, and the estimated density will be observed to be like a combination of two Gaussians and all. Like suppose in the case of normal functional way of representation, like normal parametric approaches, so we cannot represent that. You can use the only one Gaussian, we will try to fit that Gaussian to capture both of them, right. Instead, if we use the semi parametric approaches, as we know that since the data is available at two data points, we will try to impose the two Gaussians. That means we can use the two Gaussians, and the combination of those two Gaussians or two Gaussian functions, that gives you the overall density of the data and all. So, that is one example of a mixture model where the one dimensional data, where we can able to capture instead of a single Gaussian function, we can use the two Gaussians, like with its appropriate the mean vector and the spread or the variance and all. So, the same way we try to visualize that in a complex data, in a multi-dimensional data also. Like the next level, when you see that instead of one dimension, if you go for a two dimensional, suppose if you look at that the normal hills and all, where when you look at that with a naked eye, you can see that there are hills where we have like hilltops at different places and all. So, if you try to capture the, suppose assuming that that is the density and in a two dimensional plane, and if you try to capture that particular density function, so the way we can do here is that we can use the multiple Gaussians and all. We can use the multiple Gaussians, and each Gaussian will be the depending upon the data that is present at that location, we will keep the appropriate the height of the Gaussian, the mean vector and the corresponding the spread over that. So, all those things we can able to do it, and combining all those Gaussians put together gives you the overall density of the data and all. So, similar to here also in case of mixture models, the idea here is that, so here if you look at here, there are here you can see this is a one Gaussian, for example this corresponds to one Gaussian function, and likewise there are multiple Gaussians here and so on, this is another Gaussian, and here the idea here is that we can model the probability density function using m Gaussians, that is numbered like 1, 2, 3 up to capital M. There are m Gaussians with which you can able to model the any arbitrary or any complex data, and here these are known to be components, or mixture components. Here all of them have the form of Gaussian function, and then we will try to estimate these parameters of these Gaussians, estimate the parameters of Gaussian, because Gaussian means we know that the parameter will be the mean vector and covariance matrix. So, with respect to each component we will try to estimate its parameters, and then the overall density is nothing but we will combine all these Gaussians, that means by linear combination of all these Gaussians, that gives you the overall density, that is P of x. P of x is the overall density, and the P of x is realized by the multiple Gaussians, like the number like 1 to m, and here P of x by 1 is nothing but the probability density of a data with respect to component 1, and probability of x given m is nothing but the probability density estimation of a data with respect to m. So, then by combining all these probability densities with some appropriate the weight factor or mixture weights, and that gives you the overall density of the data and all. So, that you can see here the P of x is nothing but, that means the probability density of a given data is nothing but combination of sigma of j equals to 1 to m, there are m components, probability of x given j, probability of that is nothing but probability density is nothing but kind of the probability density with respect to component, individual component, probability of x given j into probability of j, right. And so, there are some m components are there. So, therefore, with respect to each component we will try to estimate this, and then we will sum up all of them, that gives you the overall density and all, right. And here the constraints will be the P of j will be summation of P of j, the mixing parameters whatever here. So, that will be j equals to 1 to m, that leads to 1, right. And so, this is nothing but the prior probabilities kind of a thing. In the case of in the Bayes theorem, when you discuss here, you can see this is somewhat relevance to that. This is nothing but a class conditional density, and this is nothing but a prior probability kind of a thing. So, similar to here also it's not instead of class conditional density is nothing but it's like the density, that means probability density of data, probability density with respect to each component, and this is nothing but weight of each component, probability of j, right. Summation over all those things gives you the overall density and all. So, therefore, the P of j equals to 1, and another thing is the P of j will be between 0 to 1. So, these are the generic probability theory constraints, and we know that probability of x given j, if you take integration over all the components, that gives you 1, that is known, because if you take the integration of all these densities, that gives you the overall density P of x. So, P of x is the mixture distribution, it is nothing but the probability density function due to the mixture model, there is a mixture distribution. P of j is nothing but mixing parameter weights, and P of x given j is nothing but component density, that means the probability of x from each component. So, the idea here is that using a mixture model or using a semi-parametric model for many choices of component density functions, so they can approximate any continuous any continuous density to an arbitrary accuracy provided the model has sufficient number of components provided by the appropriate parameters and all. So what it means here is that any complex density, any complex data can be modeled by using a mixture model or by using semi-parametric models if you provide sufficient number of Gaussians with appropriate parameters. If you can do with that, then any complex or any arbitrary complex data can be modeled close to the true density and all. That is the idea. Yeah. Here as you have seen here, as I mentioned here, the same flow diagram whatever I mentioned here, these are the inputs. Like here there are this is the input, like d dimensional data, right, and this input will be given to all the models. You can see all this model. So this is nothing but component 1, component 2, component 3, component m. That means all the inputs are given to all the models, and with that, with respect to each component, we will try to estimate the density and all. With respect to, because the entire data will be given to all the will be projected to all the components, and then we will try to estimate the component densities with respect to entire data, and then afterwards we will try to add up, we will try to combine all these component densities with appropriate weights, then that gives you the overall density and all, right. So therefore, but here the idea here is, but here the thing is that, so for a given data, this is incomplete in the sense that for a given data we do not know that whether this data point belongs to which of the component, that is not known, that means component labels are not known, because only the data is available, and then we will try to model this data using the mixture model, using the multi-component the mixture model and all. But here the component labels are not known to the data, so therefore it is an incomplete data one way. Whereas in case of a classification problem where the class labels are known, because we know that all these data points corresponds to a particular class, because that we have seen when we have discussed about the two class problem, like a class A and class B. So we have known that like these 60 examples are belongs to class A and another 40 examples belongs to class B. So all these 60 examples we have considered, and we have taken a feature vector from that, and we will try to model that using the parametric approach. Likewise the other way, other one also. So that way the class labels are available, and so we will build a class specific model and all. But here in this case we do not know the which component the corresponding data vector belongs to. So that is a problem with the in case of modeling the semi parametric approaches and all. So here from Bayes theorem we know that the probability of j given x is nothing but a probability of, that is nothing, posterior probability of a component with respect to the given data is nothing but probability of x given j into pj by p of x. This is by using a Bayes theorem, and we know that all these posterior probabilities will leads to 1, sum of them equals to 1, and probability of x given j is nothing but probability of data with respect to each component. It is nothing but this one, this particular circle, right. So these are nothing but component densities and all. So this again, these component densities we will try to model with some functional form. So here in this case, for as we know that the Gaussian will be the Gaussian or normal distribution is like easy to track mathematically and easy to formulate also. So therefore here for the analysis purpose we consider that each component is modeled by using a Gaussian function and all. So therefore the corresponding Gaussian function will be probability of x given j is nothing but this one. This is like similar to the Gaussian function, the Gaussian distribution, the way we modeled. So the same function will be used to model the individual component densities. Yeah. So now here in case of mixture model, here building the model or estimating the probability density is nothing but estimation of parameters, because here is a semi parametric approach. It means that the density, the underlying density, probability density will be estimated using a mixture of components, where each component will be realized by some generic function, some generic functional form. So therefore in the semi parametric approach, here modeling a density is nothing but, right, modeling a density is nothing but estimation of parameters. That means, for example, suppose the underlying data was there, and if you try to estimate that using 10 components, that means that suppose for each component we have some component density will be there represented by some functional form, and then estimate the parameters of all those the mixture parameters, mixture component parameters. So that all put together provides you the modeling of the probability density using a mixture model and all. And here we know again for estimation of those parameters, in case of Gaussian mixture model, we basically use the maximum likelihood technique, right. So the maximum likelihood technique means you are aware of it, because here whatever the functional form that we considered for every component, we will try to like optimize, or will try to estimate, will try to maximize the functional value with respect to the parameters and all. Then whatever the maximization, what the parameters that gives you the maximum functional value, those parameters can be viewed as the optimal parameters for a given model and all. So in that case, as in the case of likelihood framework, we know that instead of maximizing the likelihood, what the better way is that we can consider the error function, where the error function is nothing but the reciprocal of the likelihood function. So nothing but a reciprocal of, that is nothing but a negative log likelihood. So whatever L is nothing but normal log likelihood, and minus ln of L is nothing but, minus log L is nothing but negative log likelihood. It is nothing but error function. So that means here the maximization of that is nothing but minimization of error. So here for that this is nothing but the negative of there are n data points. For each n point we will try to estimate the density, right. So since the data points are independent, so therefore the product of them, and since we are taking a logarithm, so that is nothing but the summation. The product realized will be represented by the summation over all n data points. And now here the probability of xn can be written as, because this xn we are modeled by using mixture model. So therefore with respect to m components we are modeling, so therefore the probability of xn is modeled by using the summation of j equals to 1 to m and the probability of x given j into pj. This is nothing but just realization using a mixture model, what we have seen just earlier. So that way we can able to estimate the error, and we will try to minimize this error, because the maximization of likelihood is nothing but minimization of error function. And when you try to minimize that, here you can see that this likelihood function may reach to infinity, right. There exist some parameters where the likelihood may reach to infinity. When suppose if the data points falls exactly, or when the data point is equals to the mean, at that time you can able to see that the likelihood reaches to infinity, right. Because when the data vector equals to the mean, is exactly the mean coincides exactly with the data point, then at that particular location you can see that the mu minus x will reach to 0, and that gives you the the maximum the likelihood will be peaks up, like it reaches to the infinity and all. So these are the singular solutions. Similarly, if the Gaussian width equals to 0, at that place also you can see that the likelihood reaches to the infinity and all. So these are the singular solutions, and so these solutions we can able to avoid appropriately in each iteration. Whenever this occurs, then you have to replace that data point with replace that data point, so that that singular solution can be avoided. And sometimes the local minima is observed, that means a small group of points in the very close proximity can be observed. With that you can able to see that we'll falsely assume that the likelihood is maximized and all, but it's not the one, it's a local phenomena, it's not the global maximum and all. So in that case you can say that if you try to estimate that becomes a poor representation of a true distribution. So the singular solutions can be avoided appropriately, as I mentioned, that you can consider all the components having equal covariance. So with that we can able to see that the sigma equals to 0 can be avoided. And similarly, whenever the Gaussian width is shrinking, at that time immediately replace with a larger Gaussian, or you can combine with the neighboring Gaussian, so that we can able to avoid that. So usually for estimation of parameters we use some nonlinear optimization technique. That one of them is the gradient descent approach, with which you can able to estimate the parameters. And here you can see the parameters, where as in the case of maximum likelihood. So for estimating the parameters, what we can do is that the error function, for that we will take a first order derivative, and then these first order derivatives, if you equate to 0, then you can able to get these parameters and all. So this mu j cap and the sigma j cap and the other one, that gives you the these are the parameters, optimal parameters and all. But here if you want to estimate these parameters, it is not so trivial, you can see here. So, there is no direct solution to compute these things, even though you can theoretically you can able to derive these parameters, but the computation of these parameters that needs to solve the nonlinear coupled equations, because the right hand side is in turn depends upon the left hand side, because we have to estimate the right hand side to get the left hand side, but the right hand side is coupled with the left hand side. So, therefore, it will be difficult to estimate these nonlinearly coupled equations. So, it is difficult to solve basically. So, therefore, instead of computing the optimum parameters using this nonlinear optimization, what we can do here is that we use iterative solutions. We can use the iterative scheme. So, in this iterative scheme, what we do is that we will try to estimate the parameters in each iteration step by step, and every step we will try to see that whether the error is minimized or not, right. So, that way we will refine the parameters like in each step, and for every refinement we will try to see that whether there is a decrement in the error is observed or not. And in the continuous iterations, if the error is not decreased significantly or the error decrement is very insignificant, then in that case we can say that we can stop the iterations, and we can whatever the parameters are there, those parameters are considered as the optimal parameters and all. So, here you can see how do we do it. And so, here this is known to be expectation maximization or algorithm. We will see that what is that. So, here because we cannot solve these expressions whatever we have seen in the previous slide, because they are non-linearly coupled equations and it is difficult to solve. So, therefore, we do not have direct solution. So, the other way to estimate these parameters will be using the iterative scheme. So, that we are going to discuss over here. So, for that what we do is that first initially we will guess some parameters. That means, suppose we have mixture model, and assuming that we will guess some parameters. Guessing parameters is nothing but, so guessing the number of components. That means, we will assume that number of components may be either 5 or 6, something like that, and afterwards for every component we will try to guess some, we will try to consider some parameters, that is nothing but a mean vector and covariance matrix and all, and use those are known to be world parameters. That means, first step is nothing but you have to guess some parameters, or you have to consider some parameters known to be world parameters, and use those parameters and try to compute the expressions, whatever the expressions that we have seen in the previous case here. So, we will try to estimate these things, right, using the world values. Using the world values, try to compute the mu j cap, sigma j cap and p j cap. And now, these becomes the new parameters, because from the world parameters, because the world parameters means that the first time when you guess the parameters, you do not have any idea about the data, and you simply guess the parameters and use those parameters, and by observing the data you try to compute the new parameters. So, that means you try to estimate the right hand side of these equations, and those are nothing but the modified parameters are known to be the new parameters and all, and then using those new parameters try to find out the error function. That means, use the new parameters and try to find out the error function. That is, how do you compute that? So, use the new parameters and observe the data, and with that you try to estimate the likelihood, and the negative of likelihood nothing but error function, and you try to see that error, whether this error with the new parameters is less than the error that is observed in the previous step or previous iteration or not. So, that way using a new parameters try to estimate the error and see that whether the error is decreasing or not. If the error is decreasing, then what we do, you use these new parameters as the old ones. That means, using these new parameters and try to again estimate the values, estimate the parameter values and all. So, by using a data, and that gives you again some other values, some other new estimate, and these estimates, the recent estimates becomes a new parameters. So, that way every time whatever the parameters you got, so those parameters, with that parameters will try to estimate the error, and we will see that whether this error is decreasing or not. If the error is decreasing, then use those parameters as the old ones and try to estimate again, reiterate and try to estimate again the parameters So, that way here these steps will be keep on repeating until the error is decreasing and all, and wherever the error is not decreasing much or the decrement in the error is not significant, at that time we will stop, and at that time whatever the parameters were there, and those are the optimal parameters of the given mixture model and all. And here the way we estimate these parameters, compute the parameters will be, you can see here the E new minus E old. E old is nothing but error due to the old parameters, E new is nothing but error due to the new parameters, and we will try to see the difference and all, whether the difference is significant or not. If the difference is significant, then you have to go for next iteration. If the difference is not significant continuously for the previous 2-3 previous iterations, then we can stop. We say that there is not much change in the error from the last successive iteration, so therefore you can stop it. And this is nothing but here using a formula, you can say that negative log likelihood of each of the error. So E new by U old, like you can say that this U new can be estimated nothing but negative log likelihood. So that is this one, and when you take a log, this becomes a summation for n data points, right, this one. And then here the, as I mentioned, P new and P old are nothing but densities that are estimated due to new parameters and old parameters, and U new minus U old equals to this one, this expression. And here this expression, here for this expression, what we have done, we have expanded this P new, like using the Bayes theorem, we have expanded that, and then afterwards we multiplied with the P old for a manipulation purpose, and then the result will be, then after that by applying the Jensen's inequality, we can simplify this expression like this, we can simplify this expression like this. And now here this term, and here when you compute U new, this U old can be moved to the other side, this becomes U new equals to, U new is less than or equals to U old plus this something. Suppose this term we consider as some q, whatever is mentioned over here q, and this is always, this U new should be less than this one, U old plus this one. So in that case this whatever the other term, this q is there, the q has to be decreased each time, every time this has to be decreased. So for doing that, we will try to see that every step we will try to estimate the parameters, and from this, if you solve this, if you take a differentiation with respect to E new with respect to the parameters like mean, sigma and other mixing parameter, then these are the values you can able to achieve. And if you look at these values are very similar to the ones what we have observed in the solving the nonlinear equations and all. So you can see here in the case of here this is the E theta error with respect to the modal parameters, and these are the parameters and all. So when you vary the parameters, like you can say the each time the old becomes the new parameter, the old parameter, then afterwards we will estimate the data with respect to old, then you can get a new parameters, then that way this new becomes old for the next iteration. So that way if you keep on computing the parameter, refining the parameters, so we can able to get, sometimes we end up with the local minima and sometimes we may get the global minima also. So this is the way you can able to estimate the parameters, and here you can see this is the expectation maximization. So it means that we will try to estimate the error, the mean error, that is nothing but expectation step, and then we will try to minimize that. That means whether this expected error is minimized each time or not. So for that it is going to be like we will try to minimize that error so that the new parameters will be estimated. So for every step or every iteration in the estimation of new parameters, we have to see that whether the error is decreasing or not. So this is an example for the modeling the data using a semi-parametric approach. Here if you look at here, this particular diagram where the data points are distributed in an angular surface, like in an angular region, and assuming that all these data points are uniformly distributed, right, and they are like lies in the angular region, and if you want to estimate the probability density for this particular data set, so since we do not have any idea, so therefore initially we will assume some Gaussians. So here in this case we just considered 7 Gaussians, where you can see each circle corresponds to the Gaussian located at the center of the circle. So this is a Gaussian, this is another Gaussian likewise, and here the size of the circle indicates the spread, right, and the center point indicates the mean position and all. So that way here we have considered, initially we considered 7 Gaussians, and the parameters also considered some some arbitrary parameters we have considered, and afterwards by using this EM algorithm, like in each iteration, first we will initially guess some parameters. It is nothing but we guessed the model consists of 7 components and each component with certain parameters, and then this guess may be very crude maybe at the beginning, and afterwards by observing a data, then these Gaussians will be rearranged. That means the parameters of these Gaussians will be modified in each iteration, right. So, that way when the initially this is your data, and then by at the initial guess we just some arbitrarily we guess the model consists of 7 components, and each component has some arbitrary parameters. So, this is the view of the initial guess, and you can see that these two Gaussians have less spread, these two Gaussians have somewhat moderate spread, and these Gaussians have larger spread, and they are located at different locations. That indicates the mean of those Gaussians. And after performing the iterations, that means as we have seen based on EM algorithm, at each iteration the parameters are estimated, with that the error will be computed, and as the error is decreasing, keep on decreasing, and these parameters these Gaussian parameters are modified. So, as the Gaussian parameters are modified, it is nothing but because the mean vector is modified, the spread is modified. So, with that what happens, as per the data, the Gaussians also will be relocated or rearranged according to the data. So, after 20 iterations, if you observe that there will not be not much decrease in the error. So, then we stop the iteration process, and there when you look at the density, you can able to see that the Gaussians are placed like this, because this is your data, and for that initially we have using some random guess, we just consider the Gaussians like this, but later based on the EM algorithm, when you try to estimate the parameters step by step like in a consecutive iteration, you can see at the end of 20 iterations you can see the Gaussians are placed like this. So, these are almost like close representation of the probability density of a given data and all. And this particular diagram, the fourth diagram, the below diagram, this is nothing but, so here the contours whatever these are corresponds to the contours of constant probability density. That means around this contour the probability density will be constant. So, this is what your the data vectors are there. You can see here. So, along this contours it is constant. So, therefore, you can see these are uniformly distributed. So, because of that you can see the contours are like within this angular region the contours are present. So, it indicates that along this contour the probability density is almost constant. So, this way you can able to like estimate the probability density of any arbitrary complex data using appropriate number of components and all. Here we considered 7 Gaussians. In place of 7 you can consider more also or less also, but for doing that initially that is the reason that here for a case of semi parametric approaches the time that is required will be more, or you can say it is a complex one, because we have to do several trials and errors, so that out of that whichever is the optimal one we have to pick it up. So, for that for performing this trial and error ways, that takes a lot of time, and so that is the reason that the semi parametric models are slightly computationally intensive and all. So, we will stop here. In the next class we will just continue that there is another approach which is also using the EM algorithm for estimation of the Gaussian parameters. So, that will continue in the next class. So, here we will stop here. Thank you.